Hello everyone. In today's video, I will show you how to create a 12-volt power supply so we can power an ECU on the bench while repairing. I received a lot of messages asking me, do you sell a 12-volt power supply? It seems that many of you are having a hard time getting one. Actually, 12-volt power sources are all around us, and for ECU repair, we only need a power supply that can output about 4 amps or higher. That is already good enough. If you have better conditions, you can buy a professional adjustable power supply. Those power supplies allow you to adjust the voltage and the current, and they also show the consumption on a display. This will help us diagnose and repair the ECU more easily. But if you don't have one, that's totally fine. We can still use any normal 12-volt power source. The most important thing is that we have a power supply to power the ECU on the bench instead of carrying a big and heavy car battery into the workshop. Some of you also asked me, this connector box for ECU, is it 12 volts or 24 volts? Let me make this very clear. This box is only a connection interface. It does not generate power by itself. We must provide power from an external power supply. You can use 12 volts or 24 volts depending on the ECU system you're working with. So we always need a separate power source. We get the power from that power supply and then connect through this interface to power the ECU and other tools. For 12 volts, it is very easy to find. You can buy an adapter from any electronic device that outputs 12 volts and 4 amps or more. Or we can recycle a computer ATX power supply. It works very well too. For the ATX power supply to work, we need to turn it on by using the control pin. On the 24-pin connector, look for the green wire. Just like I'm showing here, it is the 4th pin from the right side. This green wire is the power on control signal. We only need to connect it to any black wire, which is ground. Then the power supply will start running. And the yellow wires are our 12-volt output. Next, I will show you another method. We will convert a normal adapter into a 12-volt power supply. These adapters are everywhere around us. They are used for laptops, for TVs, and many other electronics. But there is one problem. Most of these adapters do not output exactly 12 volts. The voltage is usually much higher. So today, I will guide you on how to lower the voltage to the level that we need. Here, I'm using a Sony TV adapter. Its output is 19.5 volts, 6.2 amps. We will use it for our demonstration. Don't worry, the principle of all adapters is very similar. Their circuit design is almost the same. Now, let's open this power supply and take a look inside. Here is the entire circuit of our power supply. To adjust the output voltage, we only need to work on this area, which is the feedback circuit. The output voltage of the power supply depends on the feedback signal that this circuit sends back to the PWM controller on the primary side. The controller will adjust the MOSFET switching based on that feedback to keep the output voltage stable as we want. So we only need to modify the feedback circuit. Let me clean the glue around this area first. Now, let me explain a little bit. This small area here is the feedback section. We have a TL431 shunt regulator right here. And this bigger IC next to it is used to automatically control the current for the synchronous rectifier MOSFET. In this power supply, instead of using a diode for rectification, they use a MOSFET to rectify the output. This method allows the circuit to automatically regulate output current depending on the load. It is a very smart design. It helps improve efficiency and saves energy. However, this IC that controls the MOSFET rectifier is not related to the voltage feedback. The feedback circuit only creates a reference voltage and sends the error signal back to the PWM controller, so it can adjust the switching and maintain a stable output voltage. To truly understand how the feedback works and modify it correctly, we need to trace the circuit and draw the feedback diagram clearly on paper. That will make the analysis much easier. Here is the feedback schematic that I have already redrawn. I will also draw the block diagram of the primary side, so you can understand the whole operation more clearly. All right, now let's talk about how this circuit works. Here we have a reference voltage network made by a 68 kilo ohm resistor and a 220 ohm resistor. The voltage is divided again through this 10 kilo ohm resistor, creating a reference signal sent to the control pin of the TL431. Based on this reference voltage, the TL431 will conduct more or less current. When the TL431 conducts, current flows through the optocoupler, and then the opto sends a signal back to the PWM controller on the primary side. From that signal, strong or weak, the PWM controller will adjust the switching of the power MOSFET so the output voltage is controlled exactly as we want. So this voltage divider is the key point. If we change its value, we can change the output voltage of the whole power supply. For example, if the reference voltage going into the TL431 is higher, the TL431 will conduct more, current through the opto will increase, the feedback signal to the controller becomes stronger, and the PWM controller will reduce the switching power. As a result, the output voltage will drop. And the opposite. If the reference voltage is lower, the TL431 conducts less current flows through the opto, the feedback signal becomes weaker, and the controller will increase the switching power. So the output voltage goes up. That's why we only need to adjust these two resistors in the voltage divider to change the entire output voltage. Right now, the power supply is giving 19.5 volts, but we want 12 volts. So we need to increase the feedback voltage that goes into the TL431, making the opto work harder. So the PWM controller will reduce output power and lower the output voltage. Here we have the two resistors, 68 kilo ohms in series with 220 ohms. Because we need to reduce the output by about 7 volts, we will change the 68 kilo ohm resistor, the high value resistor. First, let's power up the circuit and check if the power supply is working well. Warning: this is a high voltage power supply. The primary side can reach hundreds of volts. Very dangerous. Please be extremely careful when working with it. If possible, wear insulated gloves for safety. As you can see, the output voltage is 19.46 volts, so the power supply is working perfectly. Now I will unplug the power and replace the 68 kilo ohm resistor. Let's try a 56 kilo ohm resistor first. As you can see, the output voltage dropped by around 3 volts. Next, I will try a 47 kilo ohm resistor. Now we have 14.1 volts. We still need to lower it a little bit more. Let's try 43 kiloohms. Now the voltage is 13.3 volts. This is already a very good voltage for working, but I want just above 12 volts. Let's try 39 kiloohms. Oh, this value is not good. The output dropped to only 5 volts. So the best value so far is around 43 kiloohms. We need something close to 40 kiloohms. Since I do not have a 40 kilo ohm resistor, I will use two 20 kilo ohm resistors in series. That gives us 40 kilo ohms. Perfect. The output is now 12.5 volts, exactly what we need. So by adjusting the feedback resistors, you can set the output to whatever voltage you want. If you want to increase to 24 volts, you just do the opposite, increase the resistor value instead of decreasing it. And that is how we create a power supply suitable for bench testing and repairing automotive ECU and other electronic equipment. This 12-volt output can now be connected to other tools and devices to support the repair process. I hope this video helps you understand the feedback principle and shows you how to reuse available components to design the tools you need for learning and repair work. Thank you for watching. See you again in the next video.